Professor Archana Pai and Professor Dibyendu Nandi. We now have the first lecture by Professor Archana Pai. I request our director, Professor Annapurni Subramaniam, to kindly introduce her.
Yes, thank you. Yeah, so I will give the background of the speaker, but the citation and the award thing will be read out later, right? Yeah, okay. So, Dr. Archana Pai, she's currently professor at the Department of Physics, IIT Bombay. She completed a Bachelor's of Science in the University of Mumbai. Then she did her Master's from IIT Bombay, and then she did her PhD at the Inter-University Center for Astronomy and Astrophysics. And the thesis title was Data Analysis Strategies for Detection of Gravitational Waves with a Network of Detectors, and under the guidance of Professor Sanjeev Dhurandhar. Then she was an Henry Poincaré Fellow at the Côte d'Azur Nice Observatory. Then she moved on to another postdoc fellow, postdoc at CNRS, and a PDF at Italy, then at Potsdam Albert Einstein Institute, and a visiting fellow at Albert Einstein Institute, and then she joined as an assistant professor at the School of Physics, IISER Trivandrum in 2009. And she was there for a while before moving to IIT Bombay in 2017. So her research interests include multi-detector gravitational wave astronomy with black hole binaries, signal detection algorithms for gravitational wave transients, testing gravitational GR with gravitational wave observations, and multi-messenger astronomy. So welcome Dr. Pai to deliver the lecture. I hope I'm audible. Yeah, first of all, I feel very honored to be here. I wish to thank Professor Annapurni and the Peraiah Foundation for selecting me, and a special thanks to Dr. Rajni for sharing her special moments with us. Thank you very much. So with that, I will start this lecture. So the title of this lecture is Intermediate Mass Black Holes in the Gravitational Astronomy. Yeah, and basically I will begin with giving a brief introduction to gravitational waves, the field where we stand right now, and then future prospects in terms of the binary black hole detection. Okay, so the story begins with, it's almost 100 years back, with Einstein's general theory of relativity. So basically, Einstein told all of us that he essentially reformulated the theory of gravity. So earlier we knew the Newton's law of gravitation, and he gave a new picture in terms of geometry. So the gist of it is that the matter defines geometry, and the geometry decides the trajectory of the particles. Of course, the theory was sort of, the theory really was extremely successful, which sort of supported all the predictions except gravitational waves. So essentially it had new, it could explain the perihelion precession of Mercury. It gave new predictions like gravitational time dilation, which we use in our day-to-day life in terms of GPS, which all of us use when we try to book Uber and Ola and things like that. It also predicted the bending of light, so which basically means that if you have a star, let's say behind a massive object, then the trajectory of the light essentially bends, and as a result,
it behaves like a lens, and of course, we have got enough evidence of the lensing in the radar. So this is the image of from HST, where you can see the lens images of the object. Similarly, it also predicted black holes, and we know that black holes exist. I think when long back, when people were wondering that maybe it's just a mathematical construct, but now we know that black holes exist. And also the expansion of universe, we know that our universe is expanding. Now the only thing which was remaining was gravitational waves, and people were, in fact, Einstein himself was wondering whether we'll be able to detect gravitational waves. So the gravitational waves are basically ripples on the space-time fabric, and if you have, let's say, two objects, this is just an example, then according to Einstein's theory of gravity, the geometry around it essentially changes based on the dynamics of the object, and that information is carried away from the object with speed of light. So what are the properties of these waves? So basically, the waves have two polarizations. Okay, it is called as a plus and cross. This essentially depicts the strain which is produced when the waves are incident. So for example, if you have a circle, then it becomes ellipse in two perpendicular directions. So this is a plus polarization, this is a cross polarization. Okay, the waves are transverse in nature, just like electromagnetic waves. And the dominant contribution comes from the quadrupole nature. So essentially, if you have a time-varying quadrupole moment, then that system would emit gravitational waves. Now, just to sort of give you an idea of the numbers, so this is the amplitude of gravitational waves. And you can see here, there is this big term sitting here. This is a G, and there is a C to the power 4 at the bottom. And this essentially tells us that the gravitational waves are extremely weak. And as a result, if you want to really have detectable source of gravitational waves, you need to essentially go to astrophysical systems, very massive compact objects, which are making good amount of change of quadrupole moment, and that can essentially produce detectable gravitational waves. Okay, so we have a huge zoo of astrophysical sources which can produce. For example, you have binary black holes. If you have, let's say, accreting system, so if you have a black hole and let's say the matter is accreting on this, let's say if you have supernova explosion or colliding galaxies, or let's say you have binary pulsar, or let's say isolated pulsar, so there is a large number of astrophysical sources of gravitational waves which we can sort of probe. Now, since then, and with the advent of laser technology, there are two sort of instruments which are currently working. I mean, these are what is called as a LIGO detectors. So these are laser interferometric gravitational wave detectors. So these are two Michelson interferometers with the Fabry-Perot cavities, where the laser is sort of reflected multiple times and increase the effective arm length of the detector. And then basically the idea is that when the gravitational waves are incident on this instrument, then that will produce changes in the arm length, which you can measure in basically in the phase shift, and which you can sort of detect. Okay, and this strain, the H which I was talking about, was essentially strain, so that is delta L by L. So longer is your arm length, basically you can probe delta L better. So that's why you need let's say this instrument has 4 kilometer arm length, and then you have you have multiple reflections, and as a result, you can actually sort of have a build the power which is inside, which is circulating. All right, so it's very ambitious, and the detectors essentially went through various avatars, and as a result, in 2015, the sensitivity, what we call as in terms of strain. So basically, when you talk about the y-axis, you can treat it like H, which is a strain. We received a very improving sensitivity, which is almost very impressive sensitivity, which is almost like 10 to the minus 23. So here the instruments in 2015 could sort of probe H of the order of 10 to the minus 23 in the frequency band from 20 hertz to roughly a few kilohertz. Okay, so these detectors are basically, you can treat them like a bucket. So when you have a signal, when basically the frequency of gravitational waves reaches roughly value which is roughly like few tens of hertz, then the signal enters the bucket and then you observe it until sort of however the signal evolves. Okay, so it will stay till the frequency falls in this bucket. All right. So yeah, so basically in 2015, these two LIGO detectors had a very good sensitivity, and as a result, that began basically the era of gravitational wave astronomy. So it's a very young field of astronomy. It's not even 10 years old, and nevertheless we made very impressive detections in this field. So the first detection basically happened the moment we started our first observation run, which was in 12th September 2015, and we saw this event on 14th September 2015. Okay, so I think the thing which you should pay attention is the little blip which you hear, little noise, and you hear like a in between. I mean, if you want, I can sort of play. All right, so this blip which we hear is essentially a signal which is coming from this part. Okay, you can see here, this is a representation of the signal in time and frequency. So basically, as the time progresses, the frequency is increasing. It's exactly like how the birds chirp, and we call this as a chirp signal. Okay, this is called as a gravitational wave chirp. So what are the features of this? So as the time is increasing, somehow the system is producing higher and higher frequency, and then at some time it stops, which you can see here. Okay, so we did very detailed analysis of this signal, and the interesting thing is this signal was found incoincident in both the detectors, carrying similar characteristics. All right, so the conclusion was, after doing a detailed analysis, what we saw was that it was basically in spiral of two black holes. This is a sort of simulation of this event. And these two black holes, as they inspiral, basically following just the Kepler's law, and they emit gravitational waves, so they come close to each other, and then their frequency increases, which you can see from these cycles here. And it increases, and finally they sort of merge into a single black hole. And then this black hole is basically trying to settle. So the settling phase of the black hole is what we call it as the ring down signal. So basically the signal consists of inspiral, merger, and then ring down. Okay, and that's where basically the signal stops. The final black hole has settled, and that's what we see basically. Okay, so this is a typical signature of a gravitational wave emitted from coalescing compact binaries. If let's say if this black holes, if they are more massive, then the inspiral signal will be much shorter, and the merger and ring down, because that depends on our detector bandwidth. So as the mass is higher, then essentially the signals shifts to the lower frequency, and it spends very few cycles, inspiral cycles, in the detector band. All right, so what is it that we found? So we found that it was a merger of 36 and 29 solar masses located at cosmological distance. The duration was very short, and the remnant black hole was 62 solar mass. Please pay attention to the peak luminosity the signal emitted. It is like many orders of magnitude, even higher than the our luminosity of our galaxy. Okay, so it was a very massive event. It was basically equivalent to the energy emitted by 3 solar mass, if you translate it into energy in that fraction of a second. Now, please pay attention to the sky patch. So, the sky patch which we couldn't basically localize the source because the sky patch was really huge. It is almost 600 square degrees. So, the astronomers will say, hey, I mean, this is nothing. I mean, the source could have come from anywhere. But that's true. Basically, we could not localize this source. Okay, so that is just, so of course, this discovery was extremely spectacular. And the pioneers of gravitational astronomy received the Nobel Prize in Physics in 2017. So it was the first direct detection of gravitational wave, first direct evidence of collision of black holes in a binary system, first direct observation of stellar mass black holes in a binary system, and also the first direct evidence of the existence of stellar mass black hole greater than 25 solar mass. All right, so now where do we stand? Basically, we have the two LIGO detectors working. Virgo, which is a European detector, joined the network. There is a Japanese detector which is getting constructed. The LIGO India is approved, and there is another geo detector which is in Germany, which essentially is very important for developing technology for LIGO. Okay, so after that, there are 3 observation runs which are completed. The third observation run we had to sort of conclude due to COVID a bit early, and the fourth observation run has begun in May, basically last year. Okay, and we have improved the sensitivity with these observation runs. Now, what did we see so far? So, just in 3 observation runs, we have seen close to 90 compact binary merger events, and this is sort of a pictorial representation of this signal. So each line corresponds to, so each line has 3 dots. The first 2 dots are basically the component masses, and the final one is the final mass. The x-axis does not really mean much, but the y-axis is essentially the mass in solar mass units. So essentially what we see is, we have seen a large number of massive black holes in the gravitational wave windows. We have seen basically some systems which are, we have seen 2 binary neutron star systems, 2 neutron star black hole systems. We have seen 1 intermediate mass binary merger. So what about the population features of these systems? So the interesting part is, in astronomy, just from observation, we think that there is a lower mass gap in the distribution. There is a mass gap between, let's say, neutron stars and the black hole, and now we have some candidates where the final mass sits in this mass gap. So that sort of poses new question whether is there a real mass gap, or is it basically observationally observed? What kind of sources or what kind of events are the thing which fall here? Also, there is another mass gap which was scenario. But here we don't see evidence of that mass gap. Of course, there is again a bias because these events which we are talking about is actually the merger events. So it gives you indication that there are new channels of forming black holes, not just from the stellar core collapse. Okay, so when we look at the distribution of masses, then there is something interesting which we see is that there is one peak is at 10 solar mass, another peak is at 35 to 40 solar mass. So we are trying to understand, what does this peak means? Does that mean that there are lots of mergers and we are sort of seeing the signatures of that, and as we see more and more such systems, then we will try to probe these black hole binary merger events more, and as a result we might see much more multimodality here. Similarly, we see a large fraction of equal mass systems, but that is also because the equal mass systems are much more louder, and as a result you tend to see them first. We expect that when you improve the sensitivity, you will see other classes of binary black hole systems. We are also trying to understand the spins, because spins are very interesting, because the spins essentially tell us what kind of formation channels from where the black holes, binary black holes are formed. So far what we have seen is that you see basically the majority of the systems, they are aligned spins. We have some systems which have seen precision. Right. Okay, so now as far as the black hole binary formations are concerned, if you have, let's say, an isolated system, then the isolated system, you expect that the asymmetry will get shaded out with time, and as a result, your spin angular momentum will get aligned with the orbital angular momentum, and as a result, you expect that most of them would be aligned spins. But let's say if you have systems which are formed in a dense environment, like let's say at the galactic centers or globular clusters, then essentially there may not be any preferred direction for the spins, and as a result you expect that the spins will be randomly oriented. Okay, so essentially we are trying to understand the properties and hence probing the formation channels of this. So now the question is, does the observations reconcile with the models? So far, we have seen peak around 10. So if you have a isolated binary evolution models, then you expect peak to be around 10. But of course, we have also seen another peak. The dynamical formation channels, I mean, depending upon what kind of formation channel, that also sort of tells you whether you need to have multiple peaks, where you need to have. So, I mean, these essentially, the point which I wanted to make is, essentially these observations open a whole lot of new questions, like how these binary black holes are formed, where they are formed, and whether they are formed from different populations. So we expect that very soon we'll answer this question. Now, the place where we stand right now is the fourth observation run. We have so far detected 70 compact binary mergers. So we have already detected almost like 3/4 of what we observed in first 3 runs, and we expect that towards the end of the run, we'll definitely see more than 200 systems. All right, so now with this sort of bigger background, I would like to come to the kind of work which we do. So amongst this whole zoo of signals which we observed and the sources, the one which sort of prominently stood out was the 1905-21. So here, when you talk about this name, it's essentially, this is the date. So it's the 21st May 2019. That's the time when this event was observed. This was the first confident intermediate mass black hole event. And when I say first confident, in fact, is an event which is, I mean, so far even in the conventional astronomy, in the X-ray astronomy, it's very difficult to really probe or confidently say what is the mass of the system, mass of the intermediate mass black hole candidate. So what are the intermediate mass black holes? They are basically black holes which fall between the stellar mass black hole and the supermassive black hole. So the stellar mass black holes are black holes which are below 100 solar mass, and the supermassive black holes are the ones which are sitting at the centers of the galaxy, which essentially harbors the galaxy, the whole dynamics of the galaxy. And there are various ways these black holes can be formed. I mean, it can be a direct collapse of, let's say, population 3 stars, or it could be mergers of stellar mass black holes in the dense environment, or it could be multiple collisions of stars in young clusters. So there are various pathways in which you can form these systems. Of course, if you observe intermediate mass black holes, then essentially that will again tell us more about how these systems are formed, because the properties which they show are direct signatures of their formation channels. They are also interesting because we know that they are seeds for the supermassive black hole formation, and as a result, if we see more and more massive intermediate mass black hole systems, then that will also tell us about supermassive black holes and the galaxy formation. So the event which we saw was basically, it is this event. This is again the time frequency map of the event. Here you can see it doesn't have that in spiral structure, that chirping structure, because this event was very massive and it spent very less, just few cycles in the spiral phase. So as a result, the event essentially just looks like a sine Gaussian kind of profile. It just looks like a blob. And since it looks like a blob, it sort of detection of this event is a very challenging problem. And in fact, in our group, we address the detection aspects as well as the parameter estimation aspects of the intermediate mass black hole binaries. So the event was just 50 millisecond duration. It was quite loud event and it was very significant event. And what was the event? So the event was essentially 85 and 66 solar masses, which finally formed into 142 solar mass. And this itself sort of poses a lot of. So first of all, the event was very massive. It had a similar peak luminosity as the first event. Okay, it was located at the cosmological distances, quite far away. And essentially, it also showed mild evidence of mild precision, which indicating that possibly it must have come from the dynamical formation channel. The another interesting part of this event was that the component masses which were formed, okay, they basically fall into the pair instability mass gap, which essentially poses the next question, whether are these black holes formed due to the stellar collapse or they are basically remnants of the previous merger event. There might be some other merger which must have happened, and these are basically the remnant black holes of the previous merger event. And that also indicates, it gives us more confidence into the formation channel scenario, namely that the hierarchical merger in the dense environment. The another thing is about also the precision. So it showed mild precision, which also tells us that maybe it's in the dense environment, because in a dense environment you don't have enough time to sort of release or lose your asymmetry. All right. So now the question is that so this is what basically I talked about, the peculiarity of this. And this event essentially was not only, it was peculiar because of its property, in addition to the fact that it was the first confirmed intermediate mass black hole binary system. So our group actually worked in developing detection algorithm for this particular event. And the another interesting thing about this event was that when you try this, so when you have, let's say, when the two black holes are sort of merged, okay, it sort of kicks out the remnant, and they try to compute the kick velocity of this particular event. And when you try to compute the kick velocity and then compare it, some echo. Okay. And you compare it with, let's say, different kinds of, let's say, for example, globular cluster or elliptical galaxy or things like that, then essentially what you see is that this event was, so this is the prior and this is the posterior map of this. So the kick velocity was higher than the escape velocity of the globular cluster. So that also sort of adds a new piece that, is it, so what kind of, so if it is a formation channel, is a dense environment, but it doesn't appear to be a globular cluster, so there might be some other kinds of formation sort of environment, maybe AGN, centers of the AGNs, or galactic centers and things like that. So there are a whole lot of new problems which this event posed. Now, why look at intermediate mass black holes at all? Besides the connection or links to the supermassive black holes and galaxy formation, it essentially constrains the stellar evolution models, and also it helps in testing GR. So, for example, mostly for the intermediate mass black hole binaries, most of the signal is in the ring down phase where the black hole is settling. So if you actually get a very loud ring down signal, then you can probe no-hair theorem. You can try to test the black hole spectroscopy, whether how the black hole emits when it's settling, depending upon its parameter, it essentially emits quasi-normal modes, and you can try to test that. All right. So now, after talking about the intermediate black hole detection, I would like to spend a little bit time about the challenges which we face when you develop these signal detection algorithms. So as I mentioned, so these are the three phases of the coalescing compact binary. One is the in spiral, merger, and ring down. But now when you have systems which are, let's say, spinning, so you have a spin, your black hole spin is not aligned with the orbital angular momentum, then the black hole spin essentially precesses around the total angular momentum of the system, and this precision essentially reflects in sort of the modulation of the gravitational wave signal. So you see here the modulation in the gravitational wave signal, and this is what we need to really detect when we are trying to detect the system. So, so that is the problem number one. The second problem is that, so this is a spectrogram, time frequency map of intermediate mass black hole binary, and this is a noisy glitch. So as the detectors improve, we see lots of transient noise sources which enter the output channel, and as a result, there are lots of noisy triggers which look like the real signal. And hence, we need to devise techniques to disentangle the two. So, so here basically we worked on developing some special kind of noise vetoes in the wavelet-based searches, where we combine the information from different detectors in the wavelet domain, and then depending upon the noise trigger morphology and the signal time frequency morphology, we develop noise vetoes. So this is one of my PhD students. She worked on this, developing these specific kind of vetoes, which was actually useful, and it played a very crucial role in detection of this event. The other technique which we use is basically match filtering. So I'll just play a little video so that you can see what we do. So this is a signal which in red, which is hidden inside this blue data, which is a noise. And this is a template which we have, which we designed. The templates are basically gravitational wave signals predicted using Einstein's general theory of relativity. So we do correlation of, let's say, the template and the signal. And if so this is basically a phase matching technique. So if it matches, then you see a sort of peak here, and we do this with many templates, and that is used basically to detect. But the story is not sort of complete, because just doing this match filtering is not sufficient, because there are lots of noisy triggers which also trigger the template. So we developed some new sort of statistic as well as new noise vetoes. So these are basically zoo of noisy glitches. So this is another student who was involved in developing this algorithm, where we try to classify not only the signal but also the noise sort of excess energy which was used in the statistic to try to veto things properly and to develop a new statistic. And this was used in the third observation run of LIGO basically. And with that, we improved the sensitivity a lot. I mean, we could see basically with this particular template bank, we could see volume almost like 4 times more compared to what otherwise we could see. So there is, so essentially, since the signals are very weak, I mean, these specialized techniques becomes very important in detecting these events. The third thing which we are doing very recently, which is, as we know that, I mean, especially driven from the intermediate mass black hole trigger, that we know that there might be sources which are emitting in the dense environment. So we try to look for the features of these kinds of sources. Namely, when you have signals in the dense environment, they have asymmetry in terms of spins as well as in terms of masses. And if you have asymmetry in terms of masses, then they don't just emit the dominant 2-2 modes, but they also emit the higher order modes, which is like 3-3 and 4-4 and so on and so forth. So the reflection of that is, if you just draw the time frequency morphology, then because of this higher order mode, you don't just see one blob, but you see 2 blobs, or depending upon the inclination, if it is the signal is edge on, then you see this morphology even more prominently, and you see that structure appearing here. So currently our group is actually looking at that aspect. We developed a match filtering based search for looking for these specifically higher order modes. And we also developed recently a machine learning based neural network based search with one of the BTech student. So she basically used the convolutional neural network for designing, for basically separating between the glitches and this higher order mode signals basically generated by asymmetric black holes. So this is the BTech student who worked on that. So we developed a new statistic, as well as again we developed some specialized vetoes. So the algorithm which we developed is called THAMES. It's a transfer learning for higher order modes from asymmetric massive edge-on kind of systems. And this algorithm shows promise because it is able to sort of classify between the noisy glitches much better as compared to the match filter searches. All right, so yeah, so we are basically developing different approaches here. Our next step is try to include the spin orbit precision in our signal modulation and try to look for that, because I mean that is the additional effect which you expect to see in the signals. And the problem which we face is that all these three effects are not, I mean currently there are no waveforms available which can actually fold in the spin or the precision as well as the eccentricity as well as the higher order modes. So people are still developing waveforms to sort of do that, because that will give us a complete waveform family. So once that is done, then we would like to actually develop things for the complete sort of picture. All right, so this is as far as the detection is concerned. Now when we try to probe system, or when we try to detect and say, okay, this is a confident detection, then we ask the next question, what are the parameters of the system? So that's where we do a parameter estimation. And when you do parameter estimation, it's basically done in the Bayesian formalism. Okay, so you assume a particular prior on a set of astrophysical parameters, and given the data, you ask a question that what is your reformed or new information, and you try to compute the posteriors. Now, when you have a short signal, which is what the intermediate mass black hole binary signals are, then the information is very limited, and you have a very limited information, then your priors or your choices of waveforms and everything can essentially bias things very strongly. So, for example, the same system, when this group essentially, they showed that the system is, the two component masses, they are not really sitting in the mass gap, but they were actually outside. And this they could show by just choosing a different kind of setting on their parameter estimation algorithm. Similarly, this group essentially showed that it is not, it's not sort of quasi-circular system, but it's an eccentric system. So basically, what I wanted to convey is for intermediate mass black hole detection and basically the parameter estimation, when the signals are very short, then the prior choices are very crucial, and these choices of priors essentially decides your inferences. Okay, so we are trying to systematically study this issue, which we have just put it out in the archive. All right. So, what are the future prospects? Yeah, the future prospects are quite bright. We are sitting somewhere here in the 4th observation run. Okay, we expect that the LIGO will have the 5th observation run, and we are hoping that the LIGO India might join somewhere here, and then essentially that will open up even broader sort of avenues in terms of the detection as well as the sky localization. We also expect that the number of, with the improvement in the sensitivity, you will see basically much deeper in the universe by roughly by a factor of 2. And if you see much deeper by a factor of 2, then you expect the event rate goes as a volume, so basically by cube, so by factor of 8. So the gravitational wave astronomy will essentially bloom in next decade. So we just started with something like 100 events now, but you expect that to go something like 1,000 events or even more. The future is, there is already a planned NASA IISER mission, which is called as a LISA, which is the space mission. And there will be 3 satellites which are in the Earth's orbit. And then they will be, and the arm lengths are something like 1,000,000 kilometers. So as a result, you are going to observe into low frequencies, because as the arm lengths are higher, you go to the low frequency here. So this is where your LISA will be. Okay, and then there are also plans of having the next generation gravitational wave detectors on ground. These are called Einstein Telescope and Cosmic Explorer, which will be somewhere here. So our LIGO is somewhere here, and it will see much sort of deeper. So now with this, the astronomy is not just a multi-messenger, but you will do a multi-band astronomy, because there might be signals which LISA will see, and afterwards the same signal will merge in the Einstein Telescope and Cosmic Explorer. So you can actually understand the signal much better, you can localize it much better, you have much higher SNR, you have many more events, and as a result you will actually be able to probe the population of black holes, their distribution, the formation channels, all these problems you'll be able to address in future. So I think with that I'm almost at the end. So gravitational wave astronomy is in its infant state, will bloom in next decades. The black hole population, various formation channels from their properties. We also need better waveforms, but they are also expected to improve in next decade. Better algorithms, and that of course we can have much better understanding on stellar evolution models, then black hole merger, black hole binary merger density rates, population models, also to test GR, and eventually the supermassive black hole formation and galaxy formation. So this is a little group which we have at IIT Bombay. They are working on the problems which I stated. Thank you to all.
Thank you, Professor Archana, for this very interesting talk. Now I invite questions and comments from the audience.
So the bimodality in the distribution of black hole masses that you showed from one of the observations, is there something that is well understood theoretically?
No, not yet. Not yet. So I think one thing which people are trying to say is that, so let me just take it there. Here, right? I think this one. Here,
yes,
no?
Yeah.
Yeah. So this is not very well understood. One thing people are talking about is this pulsational pair instability. So because of which, you have, so when you have, let's say, the helium core mass, something between, I think there is a pileup basically. So I'll just show you the numbers. Let me just see. So when you have a helium core mass between 32 to 64, then that essentially piles up below 50. So people are thinking that possibly is because of this. Okay, but we are not seeing this. So what? So I think essentially currently this is what is the understanding, but there is nothing very clear yet because of few reasons. we have seen only one, that intermediate mass black hole, which was with the masses 66 and whatever. So there are really less number of events, okay, to really enhance that peak. So I think when you have more this thing, we'll see that. We also expect that maybe we'll see one more mode at later stage. So I mean, because see, if you have a this thing, then there has to be some gap here. Of course, though from stellar models there is a gap, there might be black holes which are formed in the merger scenario, and those will be sitting here. So, right, so you expect, let's say, stellar whatever evolution, then there are all these other merger that will have this thing, and then the next. So I mean, that is what the current understanding is. But I think all these things will settle with the next run.
Sanvid.
So you mentioned the kick velocity of the remnant black hole. So generally gravitational waves being waves, does it leave an imprint in the kind of a Doppler shift in the frequencies when they basically escape? So that is how you essentially determine that there is a kick velocity in the remnant black hole.
Yeah, yes, I mean, so I mean the numbers which I have given you, these numbers, all the properties, they are all in the source frame. Okay, so there is a redshift which you observe in the detection, but then we fold that in and we essentially give the source properties. Okay, but the kick velocity essentially you compute, because once you get the let's say posteriors on your masses and everything, okay, then you can work back and compute the momentum and everything, right? And basically that, using that you can compute the kick. Okay, so you can work it out everything, because you get all the parameters within, of course, in terms of posteriors. So you get a distribution of kick velocity, and that is what you basically compute.
And the kick velocity is relevant more where the eccentricities are more, or the spin alignments are different, or it is in
No,
the
I
case of
think-
extreme spirals.
Yeah, so yeah, so your kick velocity yeah, so when you have asymmetry, right, that's where your kick velocity is, yeah, it is more. So the asymmetry could be in various forms, this thing, but the problem which currently we have is we don't have numerical, see, all this thing is done with the numerical relativity waveforms, okay? So everything is essentially stitched. So you have the inspiral, then you have a numerical relativity simulations. Using that, the numerical relativity waveforms are stitched. The merger phase is stitched to the inspiral phase and the ring down phase, and then we get this the holistic waveform which has a numerical relativity simulation also included. So far we don't have the numerical relativity simulation which folds eccentricity as well as spins. So we have it for the precision, but not for eccentric. So we don't know about the eccentric part, but it is sort of believed that when you have asymmetry, you should have. So we hope that we'll get that complete waveform very soon. I mean, the eccentricity is a bit tricky actually, because you need, so the main eccentricity information is sitting in spiral phase, and the numerical relativists, they don't want to evolve too many orbits, unless like only specific interest is there. So because they take a lot of computational resource to evolve the orbit, right? So that is where the issue is. So, but let's hope that we get everything together very soon.
Vagish.
So just curious that what fraction of this gravitational wave detection, which are confirmed, has been looked at there, like candidates localized in other wavelengths, like electromagnetic part?
Yeah, that is only the 170870. Okay. I mean, so what happens is any confident candidate, we give out triggers. So there are alerts which happen, which anybody can sort of subscribe to, and those alerts are followed up by the electromagnetic partners. But so far, I mean, yeah, only 1708-17 has been really successful in terms of finding any counterpart. Yeah. The binary neutron star. Yeah.
Good afternoon, ma'am. So my question is about primordial black holes.
Yes.
Do you think since they can have a wide range of masses, varying from very little to very high, do you think that can give us some kind of an error in our detection or make it difficult for us to detect them?
Difficult as in?
As in, when primordial black holes are involved in a binary system.
No, so I think so far all the calculations only assume that it is a black hole. Okay, so we don't really ask a question. Okay, the only thing which it would be is that, let's say if you observe a large population of black holes, and based on the location, I mean, if they are like not in the plane or, you know, but I mean, those are, basically based on the spatial distribution, then maybe you can probe if they are primordial in nature. But not in terms of the waveforms and this thing, because that only assumes that it's a black hole.
Okay, one last question. Oh.
My question was regarding the previous localization of the events. So it is very difficult to find the optical counterpart or electromagnetic counterpart. Are there any plans on improving that?
Yes. So I don't have that slide, but actually, yeah. So I think, well, let's see. I had some backup slides. Okay. First thing is with LIGO India. Yeah. So this is with LIGO India. Okay. So so basically this is our okay, let's see. So this is a Hanford Livingston, 2 LIGOs. This is Virgo, this is Indian. Okay, so the baseline is something like 36 millisecond and 39 milliseconds. So it is basically largest among all possible pairs. So with that you will improve the localization by a factor of 10. Okay, so you can see that here. So this is your violet bananas from just Hanford and Livingston, and if you include this Indian detector, then you see all this tiny thing. Okay, so that's number 1. Okay, right. But then there are other things which you can do. For example, when you improve the detector sensitivity, right, the bucket, and when you improve the lower frequency cutoff, your signal will be much longer. And when your signal is much longer and you have and it's also louder, then you can essentially cut your signal. I mean, you can just say that, okay, I will only observe the signal up to a particular point, and then use that to sort of trigger, because then you would be observing signal a bit earlier, I mean, detecting it a bit earlier in the gravitational waves compared to this thing, right? So you accumulate the SNR much earlier, tell your electromagnetic partners that the signal is coming, and then, so this is something called as an early warning. So there are some plans of doing early warnings in the future, this thing. So you basically warn your partner earlier after you accumulate the SNR enough that there is after so and so in this patch the signal will be coming. So that's one
important.
Yeah, absolutely.
No controversy about whether it is IMPH or not. If it is an include first.
Yeah.
Location is, and it is obviously IMPH.
Yeah, but yes, no, because we don't know. Yeah, so these are all we will see.
One last question from Jason. First.
My question is related to what Vagesh was asking. So from the list of O3 events, I can see that there are 2 neutron star binaries, but we got only from GW 170817. So why is that so?
That's because the 1708-17 was at 40 megaparsec, okay, and the other ones were around 140, 150 megaparsec.
So we didn't get from any bands.
So it was, it just scales with the distance.
Okay. Okay.
As it is, the 1708-17 was also at the threshold in Fermi. If the LIGO wouldn't have given trigger, the Fermi would have rejected it. So.
Okay, let's thank Professor Archana again. We now move on to the second lecture by Professor Dibyendu Nandi. I request Professor Annapurni to kindly introduce the second speaker.
Stop sharing.
So let me introduce the second speaker, Dr. Dibyendu Nandi. He is a professor at the Department of Physical Sciences. He also is the head of the Center of Excellence in Space Sciences, India, CESI, at the Indian Institute of Science, Education and Research, Kolkata. He completed his BS from St. Xavier's College, Calcutta, MS in Physics with, from the Indian Institute of Science, and then he did his PhD there in the Institute of Science. His title being the Modeling the Solar Magnetic Cycle. Arnab, right? Yes, for So then he moved to the US to do his PDF at Montana State University, and he was there as a PDF for 2 years, and then as a research scientist for another 2 years, and then an assistant research professor for a year or so. He then later joined in 2008 the Indian Institute of Science, Education and Research, IISER, Kolkata. His research experience includes solar magnetohydrodynamics, genoma theory, solar cycle predictions, coronal magnetism, heliospheric physics, interaction of solar wind and transients with planetary magnetospheres, space weather, properties and geoeffectiveness of solar magnetic storms, etc. He has received several awards and honors. He was also a Ramanujan Fellowship. He received Ramanujan Fellowship from the DST. He also is a member of ASI IAU and AGU, the American Geophysical Union. So let's hear from Nandi about his work on living with a star. Is it the one? Okay. Okay.
This moves the slides forward. All right, good afternoon, and thank you to the Peraiah Foundation, Dr. Rajni, Institute of Astrophysics, the committee for this honor. When Professor Subramaniam was talking about the criteria and mentioned 50 years at some point, I was sitting there feeling very lucky at having just squeezed in because I just recently turned 50. So about half that time, 25 years, I've spent trying to understand the sun. I'm sure that many people about my age, or probably older, will appreciate this, that the confounding thing about science is that when you think that you're doing well, reach some sort of pinnacle, you start seeing other interesting peaks far ahead. And it's just a never-ending game. And so, I mean, I began with the sun, but hopefully by the end of this talk, you'll realize that I have taken some, diversions, and I've become more interested also in stars in recent times, and gone beyond just our immediate space environment to think about what an astrophysical ecosystem means for life. And I hope to share the journey with you today. So this is an actual observation of interplanetary scintillations measured at the UPI radio telescope, which essentially shows you this density perturbations in the inner heliosphere. The sun being in the center, the orbit of Earth, 1 AU is drawn there. So what you see here is a very dynamic and changing space environment, which seems to be originating in the sun in the form of density perturbations. What this shows you or tells you is that the space that we share with our star is not really benign as we often get an idea in our early textbook, but is a variable and changing environment which might have certain impacts on planetary space environments. Okay, if you go beyond the solar system, you can ask yourself the question that is this something that you only encounter in the solar system? The answer is no. There are many heliospheres which are known as astrospheres in other systems. And these are again observations of such system where you see that the astrosphere that is produced and sort of maintained by the plasma winds of the star is plowing through the interstellar medium with this shockwave kind of structures, which are evidence for other astrospheres, just like the heliosphere in the universe. So essentially, we inhabit an environment which is governed and controlled by a star, and this is not something that is very unique, but is something that is perhaps common across the cosmos. So, in that sense, if you want to understand other exoplanetary systems in other astrospheres, the sun, the planets, and the solar system provides you a beautiful window to this world's, whether living or not living, far beyond your own, by virtue of the fact that you can actually make relatively more precise observations of the solar system and understand them theoretically and by modeling and translate this knowledge to systems beyond your own. So that's the premise of what I've been doing, and of course I will start off with our favorite star. I hope I'll not make people upset if I say that this is the only astrophysical object that matters for us. Right. So this is the star the sun in a context of its life, and this is like the famous Astrophysics diagram that you see. So we are more really interested in the main sequence where things are stable, where a star is maintained by an equilibrium of more or less a constant source of energy due to fusion of hydrogen to helium, maintaining the balance of the star. And this is possibly also the phase of a star which provides a stable environment where not much dynamics is happening, sort of a boring phase, but perhaps a phase which provides a long enough sort of a constant background for life to form and evolve over billions of years. So I want to keep that in mind, that perhaps the main sequence lifetime is perhaps interesting from the perspective as well. Okay, so when you look at a sun-like star, we know that the energy is produced in the interior through nuclear fusion. The temperatures are extremely high, so matter is ionized into a state known as a plasma state, which is made up of ions and electrons. And then energy is transported typically for a sun-like star in the inner part through radiation, so multiple scattering and propagation of photons. Subsequently, you hit the convection zone where the plasma is opaque and therefore it gets heated up and rises, moves to the surface, radiates, and then becomes cool and then falls down. So you have convection in this outer parts of the sun, the outer 30% of the sun, much like you would see convection in the Earth's atmosphere or oceans, or even in a pot of tea that you're making. The interesting thing here, by virtue of the fact that you have ionized plasma and you have motions of that plasma here, you are really sustaining very large currents. And typically, if you do this very simple experiment where you have a current flowing and you take a small little magnet compass there, you'll see it swing, right? So if you have large-scale currents, that has a way of producing magnetic fields through the Maxwell's equations. And so we think that this outer part of stars like the sun, it's the convection zone where large-scale currents of plasma is the place where stellar magnetism is being born, and subsequently this magnetism that is born in the star comes out, permeates the atmosphere, and gives rise to much of the dynamic activity of stars that we, like the sun, that we actually observe. So I don't really want to go through many equations, but I think a little bit of MHD here. This is the very basics. So if you have a magnetic field that you are generating in a system, this follows from the Maxwell's equations and Ohm's law. this induction equation, the eventual induction equation, governs the evolution of magnetic fields, whether in a astrophysical context or also in a laboratory context where you have plasmas. So essentially, this del B is essentially the magnetic field, T is time. So if you take time to the other side and you integrate it, if you have growing solutions, then that implies that you will have magnetic fields growing. What you can do is you can think of the right-hand side term, and you can do this thought experiment. You ditch the first term, then you have eta nominal square B. That's just like a diffusion equation. So if you just set that second term, then magnetic fields will not grow. It will eventually, even if you start with the initial field, it will decay. So obviously, if you have to sustain or maintain a magnetic field or even make it grow, the first term here is important, and the first term, V is the velocity of plasmas. So what you could do is you could take the ratio of the first term to the second term, and you get this number known as the magnetic Reynolds number, which is the product of the velocity and length scale of the system divided by the diffusivity of the system. Now you can immediately see that leaping out of that is that length scales in astrophysical systems are very large. So essentially, this magnetic Reynolds number will be very high in astrophysical systems, implying that magnetic field production or creation is much more easily possible in large-scale astrophysical systems as opposed to laboratory systems. And this is why you see magnetic activity and magnetism to be so common in the universe, whereas when you produce magnetic fields in a laboratory, and there have been such experiments, laboratory experiments or laboratory dynamos, they only live for a millisecond and something like that. If you have produced magnetic fields for a few, it survives for a few milliseconds, you get a PRN, right? So that is how it goes. So it's extremely difficult. But in astrophysical systems, stars have figured this out. They do it so easily, and galaxies, of course, because the length scales are so much higher, right? Okay, so I'm not going into all this technical nitty-gritty details, but one more thing is very important. That's called the plasma beta parameter, which is the ratio of the gas pressure to the fluid pressure. Inside of stars, that parameter is very high, implying that the gas pressure is very high. So when that happens, the fluid flow or the gas essentially dominates the dynamics of the magnetic fields. So in the interior of stars, it's the flows which govern the dynamics of magnetic fields, implying that you can take the energy out of the flows and channelize it to produce magnetic fields and twist them, churn them. The exact opposite thing happens as soon as you exit the star. If you exit the star into its outer atmosphere, density falls rapidly, and therefore the plasma beta parameter plunges down to much below 1. So there, instead of the fluid flows, is the magnetic fields which is governing the dynamics of the plasma. And that is where much of the dynamism of stars like solar flares, solar storms, solar winds take part. Okay, so however, in the solar interior where both plasma beta is high and magnetic Reynolds number is high, you can easily produce magnetic fields. And I wanted to give this essence that this is simply, if you don't want to remember anything else, this is the physics we should get through, that inside of stars or in galaxies, it's very easy to produce magnetic fields by virtue of this conspiracy. Okay, now if you now think of all these different domains that you want to understand as a stellar physicist or somebody who's interested in star-planet interactions, you have to look at domains starting from the inside of a star to its atmosphere, which is like the stellar coronet, and then all the way out to planets. So so in most of these regions, magnetic Reynolds number is very high, but the plasma beta parameter takes wild swings. So interior of star where the magnetic cycle is born or magnetism is born, you are dealing with a very high plasma beta system. As soon as you're out in the atmosphere, you're dealing with a very low plasma beta system. And then when you're a little away from the atmosphere, the interesting thing that happens is the magnetic field falls off pretty fast, and the solar wind speed starts picking up. So the dynamic pressure in the solar wind or stellar winds exceed the magnetic pressure, and therefore the plasma beta parameter again becomes larger than 1. So when the solar wind or stellar winds are hitting the planetary magnetospheres or reaching this vicinity, you have again a high plasma beta. So this makes it extremely challenging to model such whole systems in one go. Typically, the tack that we take, therefore, is to deal with this as subsystems. We'll start thinking of the interior of a sun and try to do modeling of the interior of a star or stellar dynamo modeling. When people talk of the birth of CAVs or flares or coronal magnetic fields, we have separate models which work in the low plasma beta domain. And then when you think of how stellar magnetic storms or stellar winds interact with planets or exoplanets, we deal with systems which are really, again, high plasma beta systems. The one common thread is the magnetic Reynolds number tends to be very high in the system. So magnetic fields and plasmas are always frozen together and they play this, they tango together all throughout the system. Okay, so what I'll do now is give you brief highlights of our work from various domains and what we understand, what we have understood in this dark planet systems as we have come along in this journey. So the sun's magnetic fields, what you see here is a solar dynamo simulation. The sun's magnetic fields are born in its interior through the recycling of the dipole or poloidal component of the magnetic field through stellar differential rotation, which mostly all stars have differential rotation. So the differential rotation forms a toroidal or a phi component of the magnetic field from the dipolar component. This phi component, when it becomes very strong, it's subject to magnetic buoyancy, and it erupts out on the surface, producing sunspots. And then the subsequent evolution of sunspots or even helical turbulence, which twists around these toroidal loops as they're rising up, reproduces the poloidal field. So it's really a cycle between the poloidal field, dipolar field, and the toroidal component of the magnetic field that produces the sunspot cycle through dynamo action. And in each of this conversion process, you will see plasma processes like flux transport or differential rotation or helical convection playing roles, implying that the energy is drawn in from these processes to create and sustain the magnetic field. So this is a work from our group where we did the first 100-year century scale simulation, data-driven simulation of the sunspot cycle, trying to reproduce the past activity and predict the future sunspot cycle. So the black curve here is the observations, the red curve is the simulated sunspot cycle. So to see is that we do a reasonable job of reconstructing the past. And this is our prediction here for sunspot cycle 25, which is currently ongoing, which says that it is going to be a weak to moderate cycle, slightly stronger than cycle 24, peaking in fact in this year. The fact that we could reproduce the past cycles using a certain type of dynamo model known as a backprojecting dynamo model also provides a very strong support for this particular mechanism, which is always a controversy in dynamo theory, whether it's a backprojecting mechanism or Parker's Millfield alpha effect, which is producing most of the variability. We now think we have pinned it down that it's really the backprojecting mechanism which is producing cycle-to-cycle variation in the sunspot cycle. There's a bit of a checkered history in solar cycle predictions. So what you see here is the blue curve is the actually observed solar cycle and the progression of cycle 25. The red curve is the prediction by the NASA NOAA solar cycle prediction panel. Two things jump to you. One is that their prediction for cycle 25 was very similar to cycle 24, and that they predicted the peak to be in 2025. Whereas we predicted to peak in 2024, and our prediction was for a slightly stronger cycle than what they predicted. Okay, so it turns out the current solar cycle is actually ramping up faster than the NASA NOAA panel forecast, and it does look like it. Well, I'll not say anything about it because there have been surprises before. So, but we're hoping that it will peak in 2024, right? But there is an important lesson also here, because in 2018 or 2019, this same NASA NOAA panel predicted a weak cycle, but last year they have now changed their forecast, saying that there is a possibility of a very strong cycle just by looking at how this curve is rising. The problem with this forecasting, when you get multiple people in one room and try to reach a consensus, is that you're trying to build democracy out of science. It's a very wrong idea. It's really stupid if you think about it, right? You cannot take 10 different forecasts and average it out. It doesn't work like that. Right? What you can do is you can say, okay, we have a group of people, their forecast is ranges from year to year. That is still more meaningful than trying to get 10 different people who are differing on certain things and trying to get an average or a consensus out of them. It simply doesn't work. But well, so we will see how our forecast goes for the solar cycle. Anyway, so what we have learned so far about the solar cycle is this, and I'm not really getting into details of that, I'm just telling you what we have learned. First of all, we know that the solar cycle is being produced in the interior of the sun by the interaction of magnetic fields with differential rotation, turbulent convection. Variability is introduced to various effects, including turbulent buffeting of rising magnetic flux tubes, which produces tilts in sunspot pairs when they emerge on the surface. So this process is stochastic. In the sense, the convection zone turbulence, when it interacts with rising magnetic fields, it introduces stochasticity in the system. And the stochasticity is also happening in a place which is nonlinear because the magnetic fields through Lorentz feedback forces the plasma flows that are actually feeding the magnetic fields. So if you have a nonlinear system in stochasticity, we expect irregularities. And this sort of introduces variability in the sunspot cycle. So every sunspot cycle doesn't look the same, right? And this is really the challenge of forecasting. We know that the stochasticity also reduces the memory in the solar cycle, so you cannot really predict beyond one solar cycle. It's a valid question to ask, can you predict the weather up to 1 year? You can't. If you know you can predict the weather only up to 2 weeks, climatic predictions can be done for longer. Similarly, for the solar cycle, you can ask, can I predict for 100 years? You cannot. Our work has shown you can only predict for about 11 years, so one cycle ahead. So the memory in the sunspot cycle is actually not very long. And then if you ask, what is the most important parameter which is used as inputs? So what is used as in data assimilation to predict the sunspot cycle? That is the dipolar field of the sun, which has been converted to the sunspot cycle. The dipolar field manifests in observations at solar minimum, when you have the least number of sunspots, and manifests well in the polar regions, and that's obvious because in the polar regions, a purely radial component which is coming out, and you can actually nicely measure it. The problem is that the sun is spherical, it's like this, Earth is here in the plane of the ecliptic. When you're looking at the poles, you're looking at at very high projection angles. So the polar fields are actually not very well constrained. And that is one of the current problems standing in our way, which has led to concepts of a couple of different missions, which we are currently working on with US colleagues on polar flyby missions of the sun. So out of ecliptic missions like Polaris and Firefly, which is going to Solaris and Firefly, which are going to look at the sun over the high of the ecliptic so that you can image the sun's polar magnetic fields. Okay. Now, when you come out of the sun from the interior, forget about the solar cycle, now you're in the corona. In the corona, remember the plasma beta is low, the magnetic fields are dominant in the dynamics, and this is where all the fun that most of the people, including those in IISER, for example, are interested in, because this is where all the flares, all the spicules, the plasma jets, and the CMEs are being born, right? So the question is, what structures the solar corona, coronal magnetic field? It's really a beautiful place, because by virtue of the fact that the magnetic Billows number is high and the plasma is frozen in the magnetic fields, what we are seeing are really magnetic loops. This doesn't happen in laboratories, right? You cannot see them in Earth, but in astrophysical systems, you really see magnetic fields. It's just out, every time I still see it, I can't get over the fact that I'm actually looking at magnetic loops, which you cannot see in the laboratory, right? So remember, because low beta plasma, the magnetic fields are governing the dynamics of the plasma flows. So it's the relaxation, the magnetic reconnection, and the subsequent evolution of these magnetic fields after they emerge, which is creating all these different dynamics that we see going on. And there are ways to actually model that, and there are different techniques to use to model that. And again, I'll not go into details of that, but really what drives those models is you have to take inputs from the surface magnetic field. And there are various simplistic assumptions that you can build to build coronal models or have full MHD models, which gets more complicated. These models are extremely useful for looking at the birth of solar storms like flares and CMEs, which Aditya is also going to observe, the VLC instrument on Aditya is going to observe. This is, for example, from the LASCO instrument onward SOHO, the closing view there, which shows the evolution of CMEs as they take off from the sun, and also some of the plasma wind outflows moving away from the sun. So all that dynamics is happening in the solar corona. That's where all this birth is going on. And VLC is actually going to observe some of this, right? So you can model them, and this is our effort to model them. So we used a predictive scheme where we first sort of used a prediction of the magnetic fields on the solar surface, and they coupled a potential field source surface model to generate the coronal magnetic field. And this was our comparison with the observations. Remember, in the observations, you are during eclipse, you're seeing the white light, but the white light corona is really structured by the magnetic field. So the structures that you see in the magnetic field should be apparent in the white light structures, and there was a reasonably good match with the eclipse prediction as well. And of course, there is one more group in US which is very good at doing this in San Diego, which is actually a private organization of Predictive Sciences Inc. So we are sort of getting there in terms of building more realistic models to be able to predict the coronal magnetic fields as well. From the coronal when storms take off, the CMEs which have higher densities of plasma and higher magnetic fields relative to the ambient medium, they can be sometimes Earth directed. When they are directed towards Earth and they impact the Earth's magnetosphere, they generate what are known as geomagnetic storms. What you see here on the left is such geomagnetic storm, the eventual effect of such a geomagnetic storm, which induces large currents in the Earth's magnetospheric system. This is again an observation. So the point is that one of the holy grails of solar physics and space weather sciences, can you predict the impact, what an impact of a CM is going to be on the Earth's magnetosphere? Because that's the end effect that all the user communities from space science, the industry is interested in. So we have now developed models to look at the impact of CMEs on the Earth's magnetosphere. So this is a recent paper that was done by Shobik Roy. So what we do is we use magnetic flux loops, model of magnetic flux loops, which are unlike every CME, and incorporate them in a solar wind which impacts the Earth at supersonic speeds. What you see here is the formation of a sort of kind of a ring current which produces the geomagnetic storm eventually. On the bottom, you have the DST, so simulated DST index. DST is a measure of how strong a storm is for two different storms. One is a strong storm, the top one, and the other one is a weaker storm. And those curves are comparison between our simulated DST predictions and the observations, and you see that they match reasonably well, if not at all times, but in general overall for this two different, very strong and very weak geomagnetic storms. All right, so that's what we do in terms of the sun and space weather. Now I want to take a leap out of here a little bit further away and disco to stars. The sun, you have to realize, is just one star that you're seeing at a particular instant in time. About 4.5 billion, a very middle-aged main sequence star. What is sampling in terms of the sun, in terms of activity, is also very unique. There are multiple other stars with different rotation rates, different sizes, which have different magnetic activity. Now, just come back to the sun and think of the sun over its evolutionary age as well. The sun is now 4.5 billion years old. When it was about 300, 400 million years old, it was still very active, right? When it's about 7 million years old, its activity level will be different. Do we know how that is going to change? How it was when it was younger, how it is when it's going to be older? You have only one sun. How do you know that? Well, you can figure out by looking at other stars, because there are other sun-like stars in the cosmos, and you should not be blind to them, right? So let me set this premise a little bit. Why do we expect this variability? We expect this variability because the solar dynamos itself is expected to evolve over time as a star ages. The reason that this happens is, imagine a rotating body which has a wind that is moving away. As the star rotates, it is angular momentum, right? The wind is moving away, it's taking angular momentum away from it. So the star will start spinning down. In other words, the rotation period will start increasing. Rotation rate will decrease, but rotation period will increase. So it will become a slower rotator. When it becomes a slower rotator, its differential rotation also gets affected. So the amount of energy that's there in the interior to produce magnetic fields reduces. As stars age, you expect magnetic fields theoretically to fall. Is that the reality? That's the question you ask. The question is, how do you even find out what was the magnetic field of the sun much earlier? What is it going to be like in the future? What you start selecting stellar samples which are at different ages to the sun. And there is this beautiful thing, correlation, which is almost like a Rosetta Stone between the X-ray flux from stellar coronae and their magnetic flux. They're very tightly correlated. It's an extremely famous result in this field, which shows that across very large order of magnitudes, stellar X-ray flux is a very good indicator of the magnetic flux of an astrophysical system. You can use this as a Rosetta Stone and figure out how the sun's activity, for example, has varied by looking at other sun-like stars, which are G-type stars, but at different ages. By associating the star with the cluster age, you can pick up a sample, and this is what you see here. These are younger suns. There is a gap here, and then the sun is right there, and the age increases as you go. And what you can see is that there is a nice relationship between the magnetic field output, or the stellar X-ray flux output, and as the star ages, it really falls. Right? This is more recently. After this early work, it has actually been confirmed with direct magnetic field measurements by a new technique called Zeeman Doppler imaging of distant stars, which are very fast rotators. You see the same effect. You see the magnetic fields decrease with stellar age. What this implies is that the young sun would have been much more magnetically active. All young stars are much more magnetically active, and as they age, their activity evolves. The question then is, how does evolution of activity impact their surroundings and the planetary systems, including the evolution of planetary atmospheres? That's a very big overarching question that is impossible for one person or in one small group to answer. But this is something that is a very, very important question that also has strong correlations for habitability.
Dibyendu, you are talking about solar type of star or any kind of star? Because most of the planets are discovered around M dwarf star, where the magnetic field is completely...
Yeah, but that's a selection effect, right?
Yes.
That's a selection effect.
Yeah. So M dwarf star...
It doesn't mean that exoplanets only exist around M dwarfs. I'm claiming that's a selection effect.
Yeah, so you should be specific that it is solar type of...
No, it doesn't matter. I am talking in general terms. I'm not talking, not in terms of a selection effect, right? It's valid throughout. The fact that you are discovering exoplanets only around M dwarfs because it's easier to do so.
That comment is not for that. The comment is that the M dwarf star usually or some other stars also have...
See, M dwarf stars are not special. Nor is a solar-like star, right? I am talking of in general the evolution of one single star through its whatever, right?
But it's solar type of star.
Mostly yes.
Yes.
Mostly yes. Yeah, mostly yes. Okay, so then the question is, what would be the impact of such evolution of activity or different levels of activity on exoplanets? So this question has different answers, and you address these questions differently in the sense that there is both the radiation of the star, which has an impact on exoplanetary atmospheres. There is also the plasma wind, which carries magnetic fields from the star, which has an influence on exoplanetary magnetospheres and atmospheres through sputtering processes. The result of all of this is the stronger is the stellar wind and magnetic fields, usually results in higher atmospheric erosion of planets. So the expectation here is, theoretically, if the stellar magnetic field is extremely strong, you would expect a more hostile space environment and a larger impact on the atmosphere. Now, can you actually model this through the theoretical equations that you have and get a sense of if this is really true? Well, yes. We can do that, and we can start off with Earth, because Earth provides you a good window to actually check if the models that you're building are right or wrong. So what you see here again is the first star-planet interaction model produced in India. So you've seen this beautiful, models of magnetospheres in NASA websites. If you want them, you come to us. We can give it to you because now we are producing them in India. So what you see here is the impact of a supersonic solar wind on the Earth's magnetosphere and the formation of the typical bow shock that you have on the sun-facing side, on the left-hand side, and the long magneto-tail kind of structure that you typically also have observed in the Earth system. What is crucial here, and I'll try to hone on to this, is this region which is very close down there, where this solar wind is being stopped by the magnetosphere. So this is a detailed investigation of this. So what you see here is the Earth. Here is the distance from the Earth where the solar wind is being stopped in this what is known as a magnetopause, where there is a balance between the dynamic pressure on one side and the pressure on the Earth side. So if you start increasing the solar wind speed, what you see is that this balance happens closer and closer to the Earth, implying that the stronger winds you have from a star, the winds tend to penetrate closer and closer to the atmosphere of the planet and can eventually couple with the atmosphere and result in atmospheric erosion. So maybe that is the reason that we have a magnetosphere strong enough to stop the solar wind at a sufficiently far away distance from, from where the atmospheric extent is, which is about 100 kilometers for the Earth, right? So this is actually something that is very important. You can also actually use somewhat variants of this model to look at how is the environment around moons. When I started doing this, it was inspired by the class team on Chandrayaan 2. They were having some intriguing observations of spikes when they're doing transit through the magnetotail during full moon. And they couldn't find any explanation for this. This is the first model in the world you are seeing of solar wind, the Earth, and the Moon in the same system. What we see here is this very intriguing structures forming around the Moon. The Moon is right there, that small little thing there. These are current sheets. And we have discovered through this model there's a ring of current sheet around the Moon. And whenever the spacecraft samples that, there's a spike in energetic particles. This is something that we have sort of figured out, and this is now being written up for publication. So actually, you could extend this space environment models also to study moons of star-planet systems. One very intriguing question is the red planet. What happened to Mars? When Mars was very young, it had a liquid iron-nickel core, which was thought to be fluid and rotating, and it was thought that Mars had a magnetosphere, and also an atmosphere which was sort of warm and moist and perhaps conducive to greenhouse effect and the possibility of life on the surface or the atmosphere. But then in between that about 1.5 billion years and now, Mars lost its core rotation, the core froze, and its global magnetosphere is also gone. And intriguingly, its atmosphere is also no longer there, right? So you don't see, the atmosphere is I think about 100 meters or something. Most of it has been lost. People wonder how did this happen. So you can extend the kind of study that we're doing, and this is exactly what we did, to look at a Mars with and without a magnetosphere. When you have a magnetosphere, you see this sort of bow shock region where the magnetosphere stops the solar wind. When you don't have a magnetosphere, the solar wind magnetic field and the solar wind plasma really goes very close to the Martian surface, wraps around it and slips past it. When that happens, there is viscous coupling between the solar wind plasma and the atmosphere of Mars, resulting in the mass loss of enhanced mass loss of the planet, which might explain why Mars does not have an atmosphere today. So this is kind of similar, so I will not go through this again. It sort of explains how this solar wind couples to the atmosphere and pulls out the atmosphere slowly. You can again go back to theory. We want to kind of, formulate a very generic theory for this. The theory really is very basic if you come to it. So you have the stellar wind, which is impinging on the planetary magnetosphere. How do you achieve a balance? The balance is essentially a pressure balance, right? Balance of forces due to pressure. The stellar wind side, you have the dynamic pressure, so half rho v square. Faster the wind moves, higher is its density, higher is its pressure. That plus the thermal pressure, which depends basically thermodynamic, thermal pressure, plus the magnetic pressure, because the magnetic fields also have pressure associated with it, and the magnetic fields are also moving with the plasma from the star. On the planetary side, you have only the thermal pressure and the magnetic pressure, where the magnetic pressure comes from the magnetosphere of the planet. When you can achieve that balance, then you have the formation of a magnetopause. It's really this which governs all these dynamics. And you can do a general study for any star-planet system with arbitrary magnetic fields to figure out how it is. This is one of the simulations of this. What we observe while trying to do this very arbitrary general study with different magnetic field configurations is when you have very strong magnetic field of a star and weak magnetic field of a planet, the magnetosphere is really ripped out in the form of wings being cut out from the magnetosphere in the form of wings which are actually known as Alfvén wings. It looks good, but it's not good for the planet, because when you start forming Alfvén wings, mass loss starts happening not only from the front but also from the magnetotail or backside, because it opens up and the backside of the atmosphere is also exposed to the wind plasma. So what you see here is the mass loss rate on the y-axis versus the ratio of the planetary magnetic field to the solar wind magnetic field. And these are dots. These dots are results of different simulations. And you can construct a theory, an empirical relation, a theoretical relation from essentially this understanding and put them together. And you see that the simulations beautifully match the theory that you have come up with. And this is something that we established very recently. I think it was published last year. Surprisingly, I wanted to note something here. So it's, this is expected as the planetary magnetic field reduces relative to the stellar wind magnetic field. So you come to the left of the plot, the mass loss increases. Right? So that is expected because the magnetosphere is becoming weaker and the stellar wind magnetic field is becoming stronger, you expect more mass loss. What is unexpected is this, that for different planetary systems, if you go across these different curves, if you have a planet with a stronger magnetosphere, it has a stronger mass loss compared to a very weakly magnetized planet. The reason is that if you have stronger magnetic fields, you have larger sites for magnetic reconnection, and magnetic reconnection really opens up the magnetosphere, resulting in larger mass loss. So this is the last slide I have. So sort of kind of giving a sort of broader picture of this. You have a star and you have a planet. And this planet actually is cocooned within this magnetosphere. And it's really the properties of the stellar magnetic field, the stellar activity, and the properties of the magnetosphere, which depends whether, which governs whether this little cocoon that you have, which is the atmosphere that allows you to survive or live, is going to stay with you or not. If you lose it, there is no life. If you can sustain it for a long enough time, you have life. So here is my very provocative postulate that other than the usual things that you think of, like oxygen and water and a biosphere, is the relative magnetic field strength of the star that you are going around and the intrinsic magnetic field strength of your planet that has also an important role to play in the possibility of life in a planet. And in case you have missed my whole talk, this slide is fine. Thank you very much.
Thank you.
Thank you.
How to sustain the magnetosphere around them?
So for sustaining a magnetosphere, you need, so dynamo is similar in the sense you need to have fluid motions. Unless you have motions, you don't have the kinetic energy to draw out to form magnetic energy. So if you have a solid, for example, you can have a conductor. You can even have a superconductor. But if there is no motion, you are not sustaining a large scale dynamo.
That is not in our hand.
That is not in our hand. I mean, see, for example, how can a core become solid? As long as you have high enough temperature, it will not be solid. That's one thing. But the core also have to have sustained convection. The way you sustain convection is to have a temperature difference across different layers. So if you become a constant temperature core, there will be no convection, no motion, then that also is useless, right? You can't produce an atmosphere. I don't think we can geoengineer this. This is such a large scale. I mean, some things you just feel you are damn lucky. That's it.
There was a Parker probe which went very close to the corona.
Yes.
Did you see any of those images? It went very close to 1% of the.
Yes, I mean, we've seen those images. So Parker solar probe was designed to reach. I mean, it was touted to reach the outer parts of the corona. Where is the outer part of the corona? I can claim that it's in the end of the heliosphere because the sun's atmosphere is expanding out into your wind into the heliosphere. So there is no well-defined boundary of the corona, but then there is there is Alban radius. So if you can reach within the Alban radius, then perhaps you're in the corona. So, but I don't think it reached inside the corona, but it is in the region where the solar wind was still being accelerated, certainly being accelerated. So it was designed to answer essentially the heating of the solar wind and its acceleration. So that mission is still ongoing, but it is, I think, not yet reached the closest. Has it reached the closest? It's going around in orbits. So I think the closest approach has not yet happened. It's yet to happen.
Two questions.
You said that the solar type stars, at least, they are their magnetic field and it means magnetic activity shrinks
Over time.
With age, yes. It means that astrosphere also shrinks.
Very good point.
And this is very bad for our like life on Earth.
Right.
It's actually known case that something like several million years ago, astrosphere, our heliosphere shrunk. And there is even some radius which is called about the radius beyond which anything from outside all the galactic cosmic rays and whatever supernova, it will kill the life on Earth.
So there are two things here, right? So if this glass is sliding, okay. Yeah, so if the solar magnetic field is lower, over time it gets lower, the astrosphere will sink, because it's true, because the magnetic pressure is shrinking and then interstellar medium pressure will start dominating, right? But then also, I mean, eventually the sun is going to become a red giant, the next time, right? Question is whether we killed from the outside shrinking or the sun expand, right? Make a choice. I don't know which one would you love to do.
Yeah, it's interesting about this. What comes first?
Yeah.
Sooner. What comes sooner?
Where is the magnetopause of the Earth?
Magnetopause of the Earth varies depending on the solar activity and where is the exact Earth's position in its orbit around the sun. Typically within about 5 to, I think, 10 Earth radius. Well beyond the atmosphere. So the atmosphere is very well protected.
So beyond the ionosphere?
Yeah, of course, well beyond the ionosphere also.
Okay, the second question is that have you calculated what should be the maximum ram pressure of the solar wind that may destroy the Earth geomagnetic field permanently?
Yeah, so that is a good question. The point is, can you really destroy the Earth's magnetic field permanently even with a very strong solar storm? What you can do, you will not be able to. What you can do is by reconnection, you can get rid of all the field in the magnetosphere, because you can have, it's just simply flux conservation. If you just think of it very simply or naively, if you have enough flux in the solar wind, magnetic flux in the solar wind, which is oppositely directed compared to the Earth's magnetic field, then it will cut through the magnetosphere, resulting in a temporary hole in the magnetosphere while this big, huge storm is going through. But the energy density in the flows in the Earth's interior is still much higher, and it's long-lived, right? So you will not kill the dynamo. So it will again fill up with magnetic fields. So those effects, in fact, are known. That when there is a strong solar storm, there could be a void in the magnetosphere, but it will not get permanently destroyed.
Yeah, you mentioned about two missions to study the poles of the sun. How are they different from the Ulysses mission?
So Ulysses mission had a big problem. The Ulysses mission didn't have this one instrument that would have really been very useful, which is the basically what is known as a magnetograph. You can measure the magnetic field. So if you need to measure the polar magnetic fields, you need to have a magnetograph instrument. Ulysses was good for solar wind. Look at how the solar wind varies across the different heliospheric latitudes, but it had no magnetic field measurement instrument for the sun's magnetic field.
You mentioned about the inability to predict the solar activity cycle beyond one cycle. Can we use the stellar activity cycle of different stars, different ages, that information to predict more than a 2-3 cycle?
No, you cannot. I mean, so we know that the inherent stochasticity in the solar cycle will simply remove any memory over long scales, and every star is having its own, different system with different stochastic perturbations, different dynamos. So there is no way that you can compare this, because you're comparing apples and oranges. You cannot look, because there is no pattern to it. Right? If there's a pattern to it, you could have looked at past solar activity itself and said, okay, these 2 cycles is looking like those 2 cycles that happened in the past. So the next cycle must happen just like what was the next cycle after those 2 cycles in the past. Never happens like that. We can't even do that in the solar cycle. There is no pattern. Even for the same star, the pattern doesn't repeat. So you cannot use another star to figure out what's happening, let's say 100 years ago.
There is a recent report that Proxima Centauri has a 7-year cycle.
Yeah, but yes, I mean things are different. But you can say, by looking at a star which is 1 billion years older than the sun, you can roughly say what the sun's activity is going to be like 1 billion years down the line. That's different from solar cycle prediction, right? It's like you're now going climatological, right? As opposed to being like weather.
Yeah, so I have two questions. So one is like when you mentioned that early sun was more active in terms of plasma flow and solar wind, but at the same time radiation output was quite less. So if we put the problem like young sun paradox, so in that most of the time literature discusses only the radiation output and then early Earth had water. But if we include in that this plasma solar wind coming, how this problem gets complicated or simplified to solve that?
Well, so the problem is the faint young sun paradox. The problem that as I understand is how did Earth continue to have a liquid ocean and all that, right? When the sun was faint. There have been theories of other kind of heating, like for example UV radiation related heating, because that you expect to be stronger. Even the overall
the greenhouse effect was much more higher at that time.
That is also the other theory. That's not the astrophysical thing, but that's also another theory. And then there is another theory of life having emerged in cold place like the lakes of Antarctica, as opposed to in a hot place. So there are multiple different hypotheses for trying to figure out how life could have emerged under the circumstances.
And regarding your simulation of solar wind interacting with the Earth magnetosphere, I'm just wondering in that whether it's the steady solar wind or the CME has also been inserted to see that.
So this was a steady solar wind. This one was steady solar wind impacting the Earth's magnetosphere. The one that was before this, that was a CME. I didn't show you the simulation, just the Earth impact of it. But if you're interested, I can show you the simulation. So that is a CME flux slope being carried by a solar wind, which is impinged on the Earth's magnetosphere. And the CME flux slope, by the way, the properties of CME flux slope are determined based on ACE and wind observations as input to the model. So if the magnetometer instrument on Aditya works, then the magnetometer instrument will give us those profiles, which can be used for making these predictions. I'll not call it prediction because it will be too late, because magnetometer only measured 30 minutes before. This simulation takes 2 days to do. So
there is an interesting correlation between the rotation of the stars and the magnetic field, especially in case of stars which are more massive than the sun. So those with larger values of magnetic field have slower rotation. But I gathered from your testing that it was the opposite in this.
No, so dynamo theory poses that if you have rotation rate, so if rotation rate is faster, then you should have stronger magnetic fields. And that is because there's a number called Rossby number, which is the ratio of the star's rotation period to its convective turnover time. So you can actually mathematically show that the dynamo number goes as inverse. I think the Rossby number is the inverse square root of the dynamo number. They're inversely correlated.
But in this case of stars, magnetic stars, it's the opposite.
No.
They are more massive than the sun.
Okay, so I'm not sure about this.
But the big
kind of stars.
magnetic star rotation is very high, very fast.
You're talking of magnetars. Sorry?
Peculiar
stars. So you may have This theory works only for sun-like stars which have a solar-like alpha omega dynamo. It will not work for those kind of stars which don't sustain this kind of dynamos.
But you have an example like Venus has no rotation, so Venus has no magnetic.
Yeah, but I will not compare Venus with a star, but
Potential core, everything is similar to Earth, but its rotation is almost zero. So there is no magnetic.
Okay, so let's thank the speaker.
The last question. It's a nice question. Has anybody looked at you showed this graph of magnetic field versus age.
Yeah.
In contrast, looking at the long-term evolution of magnetic fields, has anybody looked at magnetic field versus color or key effective?
I'm sure people have, but I cannot tell you off the head. That's an interesting question though. And that will be related to the size also of the star.
Yeah, I
Right?
thought you were looking at only stars, sun-like stars.
These are sun-like stars.
Just one color.
No, he's talking of something else. No, he's talking, has somebody looked at others?
Okay,
Yeah,
other
yeah.
stars.
Yes, I'm sure people have, but I'm not aware of it. But I think people would have, I think.
But there are other problems there, like you have ages and, you have to have separate parameters identified and then it's a function of it, right? Because in the case of massive stars, the color variation is not much, but in lower mass stars, the isochronous concept tends to change. So you have to actually model what is expected and then look for unexpected.
Just as a survey.
I mean, in this game, the age is the most difficult thing to figure out. If you get X-ray flux, that's a very good indicator of magnetic flux, not a problem. But age is very difficult. Sometimes, if you have a good handle on the rotation, for solar-like stars, it's possible to use gyrochronology. I'm not sure it's possible to use gyrochronology for peculiar stars or no. That's probably not.
The other problem is peculiar stars, A-type stars, at 1.2, the whole thing changes. Like the sun has a convective core and radiative core and a convective envelope. But for stars more massive than 1.2, it changes to a convective core and radiative envelope. So then the
whole thing still changes, completely changes. Yeah.
Yeah, that would be nice what Arun says. Among K-type stars, different ages, G-type stars.
That can be done.
Yeah, but metallicity will be different. It is a problem also. It will be bluer.
Yeah, it takes same metallicity.
See, but it's
All the
clusters.
stellar fields is nice.
For
That's nice.
Okay, so
Thank you very much. Thank you.